All right, so I start this talk with two bad news. The first one is that if you came to this talk for React server components, there are not going to be any React server components in this talk. They did not fit in. The second bad news is that we, as React developers, are bleeped. They would ban me otherwise if I said the word. But this is the PageSpeed Insights report for NewYorkTimes.com. You can see that all of these performance metrics are green, except the interaction to next paint. This is the PageSpeed Insights report for Target.com, a big American e-commerce written in React, just like NewYorkTimes.com. All the PageSpeed Insights metrics are green, except the interaction to next paint. This is the Notion website. Again, all the speed metrics are green, except interaction to next paint. This metric, interaction to next paint, is a new performance metric introduced by Google. It measures how fast clicks or keyboard input are on the page. And in almost every React app or website I've seen so far, this metric is yellow or red. And also, this metric becomes a core vital in March 2024, which means that just in a few months, your CTO, your boss, or your marketing team will also become suddenly aware that this metric is yellow or red. Now, who here has worked with this metric before? Has anyone tried optimizing it? I saw one hand. Okay, well, then let's take a really quick dive into theory. And to talk about theory, we would need to cover three things: the interaction to next paint, and the interaction to next paint for the page. So here is a React app. It's a simple note-taking app. I could take notes. I can see actually if I'm typing. I can take notes, I can open notes, I can create new notes, and I can filter notes. And the filtering notes interaction is slow. If you look at the spinner that spins in this corner, which spins when the page is idle, which freezes when the page also freezes, you would see that whenever I type into the filter, the spinner freezes for a second. And this is a slow interaction, and this is what makes the interaction to next paint bad. Now, I can feel that this interaction is slow, but I don't know how actually this interaction is slow. I don't know how actually it affects interaction to next paint. I don't know anything about interaction to next paint, right? So one thing I really like to do to see how fast interactions are and to see how they affect this new metric that Google has introduced is I like to go to the Chrome Web Store, install the Web Vitals extension, go back to the app, whatever app I'm running, open extensions. Oh, wow, I cannot see from here. I can, oh yeah, I can see. Hold on, I need to open the Web Vitals set. Let me do it differently. Yeah, I cannot see where the second one is. So yeah, this is better. So I need to open the extension settings. I need to enable console login, save settings, and then open the console. And at the moment I do that, and the moment I try doing anything in the app, I would see the extension log every interaction I make on the page. Like whenever I click something, I would see how long that click took. Whenever I type something, I would see how long that typing took. And whenever I tried to type into my filter input, I would see how long that filtering action took. I would see that every time I type into the filter input, my interaction takes 700, 600 milliseconds. And I could see that as the interaction goes higher and higher, so does the INP, interaction to next paint, value also does. So what interaction to next paint basically is, the new performance metric that Google introduced, it's the slowest interaction that happens on the page during a single user visit. So I'm a user, I go to an app, I do a bunch of interactions with the app, I click stuff, I type stuff, and the slowest key press, the slowest click out of this is going to become the interaction to next paint metric that Google measures. That's going to be yellow or red, and that's going to create a lot of issues for us in just a few months. So now this was the interaction to next paint just for a single visit, but what Google shows is the interaction to next paint for the whole page. So how does Google derive this number? The way it works is if you opted into sharing data with Google, what Google actually does is every time you go to any website and click on that website, Google collects every INP value from that website. For that visit, it takes all these visits, it sorts them, it picks the slowest 25% of those visits and names the fastest of these slow 25% of visits as the INP for the page. So once again, what INP is, you measure every interaction, you pick the slowest one, then you collect all the slow visits, you pick the slowest 25% of all visits, and you get the INP for the page. And this INP for the page is yellow or red in almost every React app I've seen. So, well, now let's get back to our app. Our app is slow, and this makes INP also slow. And if I were to debug this issue, I would see that this issue, this slow typing into the filter, is caused by a reactor render. Here's what's happening in the app. So when I type into the filter input, what happens in the app is React calls this set filter function, which is a useState hook, that changes the state in a bunch of components, and that causes React to render all these components one by one until it's done. And this is what makes my input slow. This re-rendering is a stop-the-world operation. Nothing can happen until React is done. So when I type on the keyboard, the page won't update until React has finished processing all the components, right? If it takes 2 seconds to process all the components, then the page won't update until 2 seconds later. This is the classic slow React render, and this is what makes interaction to next paint bad in React apps. Now, we have a performance problem, right? I type into the filter input, and the app freezes for a second. This makes the interaction worse, this makes the user experience worse, this makes the INP worse. Now, my question to you folks, if you are a developer of this app, how would you try to optimize this? How would you try to make this faster? Spoilers. Any other ideas? Debounce, what? Yeah, well, so yeah, there are a bunch of stuff you could do. You could try wrapping some stuff with React memo if there are any components that are rendering unnatural. You could optimize the component. You could virtualize the list if that's a big list, and that's a big list. You could debounce on throttle. You could, and one more thing that you could do, which React introduces, you could also make updates non-urgent by using useTransition. What does this mean? So with React 17 and below, every update that happens in the app is considered urgent. If you click a button, React has to handle the update immediately. If you type into the text field, React has to render the list of nodes immediately, and that's a stop-the-world operation. With React 18, however, your updates can now have a priority. Every update you make in the app is still by default urgent, but what React now also supports is non-urgent updates, and non-urgent updates almost magically don't block the page, no matter how long they take. Let's see how this works. So here is the code for my left sidebar in the app. There are a few critical bits here. I have the few critical bits here. I have the useState hook that controls the state of the filter. I have the filter input, which renders this input. I have the list of nodes, which renders this nodes. And right now, every time I type into this filter input, the useState hook updates, and that causes React to render the whole list of nodes and do a really slow interaction. So what React 18 now allows us to do is React 18 allows us to take some part of the update and tell React that, hey, this update is non-urgent. And the way you do that is you do it by using the useTransition hook. So let's do just that. So to apply useTransition here, I'm going to make several changes. Bear with me. The first change that I'm going to make is I'm going to take my single bit of state called filter, and I'm going to split it into 2 bits of state. I'm going to call them filter input and filter value. The first one is going to control my input component. The second one is going to control my list of nodes. This one is going to be called setFilterInput and setFilterValue. Now, I need to take these two new bits of state and I need to make them actually control the bits of the UI that I care about. Done. And now I need to set both of these states whenever I actually type into the filter, right? So I'm going to do this. Perfect. So far, what this would do is this wouldn't really do anything. I just took one bit of state and I split it into two bits of state, and that makes 0 sense, right? I'd still type into the app would be slow, and now for some reason I have 2 bits of state that store the same thing. However, what I can do now with React 18 is I can take one of these bits of state and I can tell React that, hey, when you update this bit of state, the bit of state that controls the list of nodes, please update that bit of state non-urgently. Because I don't care when that update completes. What I care is that the filter input updates urgently, because that's where the user types and that's where the user should see the input right away. What I don't care is if the list of nodes takes longer to update, because the user can wait. And I do that using the useTransition hook. So let's do just that. To tell the update that the setFilterValue hook update is non-urgent, I need to do the following. I need to import useTransition. I need to call useTransition inside the component body. I need to retrieve the isPending and startTransition functions. isPending value and startTransition function from the useTransition hook. And I need to wrap my setFilterValue setState with startTransition. Oh, yes. Transition. Okay. Oh, that's why I didn't. Okay. That's why you use ESLint. So, all right. So the change that I've just done is the single change that I've just done is I took my setState function and I've wrapped it with startTransition, right? And if I remove that, if I just type into the filter, you would see that the filter is still typing into the filter is still slow, right? I type into the filter and it freezes the page for a second because React has to render all these components, and that takes a lot of time. Now, if I wrap this setFilterValue with startTransition, what would happen is I would type into the filter input and the page would not freeze anymore. I type into the filter input and the page is completely responsive. You could see I'm typing and the spinner is spinning. And I'm typing more and the list of nodes renders. And it actually, if the render is cheap, it renders right away. You could see that there's no delay like with debouncing or with throttling. It handles the input right away. If the render is cheaper, if the render is expensive, it just runs the render non-urgently. So this is really, really cool. And the page stays completely responsive while the expensive render is running. This is almost like magic. Now, does anyone have any idea of how this works? Close, no. Any other ideas? Actually, no, but yeah, you're thinking in the right direction. So the way this works is, sorry, wrong slide. The way this works is giving back control. So React starts rendering the app and then gives the control back to the browser after every frame. It does not use request animation frame. It does not use request idle callback. It uses a slightly different mechanism. And let's see how exactly this looks, which mechanism exactly it uses. So under the hood, here's how useTransition works. React has a queue of updates. In our case, this queue has components that don't need to be updated urgently. It's nodes lists and a bunch of node buttons. React also has a function called perform work until deadline. This function takes the update queue and processes it one by one. And in React 17, this was pretty much it. You would start processing the queue, and you'd keep processing the queue until you are done. And if this takes 2 seconds, if you need to render 2,000 components, then this would take 2 seconds, and you would render 2,000 components. All this time, the page would be blocked. Now, what React18 did is React18 added 2 critical changes. First, in the while loop, it added a check called should_ill to host, which tells React whether it should give the control back to the browser. And second, after the loop, React now checks whether there are still any pending unprocessed updates and schedules another perform work until deadline function to be executed in the next frame. Now, should_ill to host, the function that decides whether React should return the control back to the browser, is actually one-liner. It simply returns true if the current render has been taken more than 5 milliseconds. And schedule perform work until the deadline function, the function that schedules the next 5 millisecond chunk of JavaScript activity, is also pretty simple. It does not use request animation frame, because that would run not frequently enough. It does not use request idle caller, because it has a minimum delay of 50 milliseconds, I think. But it just calls set timeout 0 to schedule the next performed work until the deadline call. Or if set immediate or message channel are supported, it uses them instead for the same purpose. And that's pretty much it. That's how it's implemented. If you remember the slide from the past, this is how React17 behaved when I tried typing into the filter input. Right? I typed into the field that changed the state in a bunch of components, and React rendered all components in one single pass, freezing the page for the whole time. Now with React18, this changes. When I try typing into the filter field, React calls setFilterInput, and then immediately after calls setFilterValue. This causes the state to update in a bunch of components, but now some of these state updates are marked as urgent, whereas others are marked as non-urgent. So what React now does is it still renders the urgent updates in the old blocking manner, but then it starts rendering non-urgent updates in a non-blocking way, giving the control back to the browser every 5 milliseconds. And because the browser gets the control back, it can repaint the page much sooner. The first interaction is going to be faster because we aren't blocked by all the non-urgent components. And subsequent interactions are also going to be faster. So, like for example, if the user clicks a button again if the user clicks some other button during the non-urgent interaction, during the non-urgent render is not going to take longer than 5 milliseconds. So the on-click event handler and the next paint is also going to happen in no more than 5 milliseconds, which keeps the interaction to next paint metric low. This is the concurrent React render mechanism, and this is how it improves interaction to next paint. Now, what we talked about so far was just one feature that helps with INP. It's useTransition. There's also another concurrent feature that also helps with INP, and it's Suspense for React hydration. So if you're not familiar with React hydration, it's a process where you server render a site, then on the client you hydrate that site, rendering every component again, attaching event listeners to the already existing DOM, and you get a live site. And hydration, in my experience, is typically the most expensive JavaScript operation that a React app could have. Like, for example, here's Deliveroo spending 1.55 milliseconds hydrating the site with 4 CPU throttling. Or here's Notion spending 1.8 seconds. Or here's Walmart spending 1.1 seconds. And I don't mean to say that these websites or these teams are bad. This is a standard situation because hydration has to render every single component on the page. And because it does it in the standard blocking manner, that keeps the page frozen for a really long time. Now, what React18 allows you to do is it allows you to take your site and hydrate it concurrently. To do this, you need to take your page, like, for example, this Notion landing page, split that page into sections, like a header, a hero block, more sections somewhere further down, and wrap each of these sections with Suspense, which would basically look like this in code. You don't even need to specify the fallback, just the Suspense tag. And what would happen now would basically be following. You would call hydrate root, React will start rendering components one by one until at some point it stumbles upon the suspense boundary, which marks non-blocking hydration. And when React stumbles upon this boundary, it won't proceed past that boundary just yet. It would keep rendering the remaining urgent components until it's done. And then, only then, once it's done, we'll render the non-urgent ones, giving the control back to the browser every 5 milliseconds, just like with useTransition. And this is what helps INP a lot. Now, you might ask, okay, if this is so good, if this makes the page hydrate non-blockingly, why do I need to bother with splitting the page into sections? Why don't I wrap just the whole page with suspense? And the answer is that it would actually flop your INP. Why? This has to do with another suspense behavior from React 18, which I call forced urgent hydration. There's no official name, just my name. The challenge behind it is the moment you click some suspense boundary that you have in your app during hydration, React switches that suspense boundary to urgent hydration. So if you wrap your whole page with suspense, it will hydrate like this 5 milliseconds at a time, right? But then if you click the page right when it's hydrating, what would happen is React would switch to the urgent hydration for the remaining part of the page. So you would click the page and the page would become frozen. It would basically work as if you didn't have any suspense at all. Which means the next paint won't happen until that urgent hydration is complete. Whereas if you wrap separate page sections with suspense, which will give you rendering that looks like this, and then click some suspense boundary, then only that suspense boundary will hydrate urgently. And that will be much faster, and that will make the next paint happen much earlier as well. So this is why you don't want to wrap the whole page with suspense. All right, so this is interaction to next paint. This is the two big React features that help with interaction to next paint. This is how they work. And this is how they help. So take them, take your INP, and go make your INP green. Thank you.